traffic. We really appreciate you coming out tonight and spending time with American Physical Society and our lovely panelists. A couple of housekeeping items that we really appreciate. So one of the things is we have lovely, amazing giveaways on the right. So when the panel is complete, feel free to grab some APS tchotchkes. We have survey QR codes throughout the room, as well as we'll email everybody tomorrow morning. We value your feedback, so if you can provide some feedback on your experience here at our 4th APS meetup, we'd really, really appreciate it. We'd love to continue the series. That being said, I'll introduce myself. My name is Marcia Maxwell. I'm head of corporate relations at American Physical Society. We've been around, I think most everybody's familiar with APS, but we've been around for about 125 years. Our role is to make science open for all. So we do that by connecting industry and academia together to advance science in the world. And we're very proud of that. We do that through our journals and through our meetings. So we really appreciate your coming to what is our 4th Austin Community Meetup that started last June. I want to say a big thank you to our contributing sponsor, ORCA Computing, and T, who's our moderator today, for his support the past couple of meetups. He has been an amazing partner, as well as our panelists, who will do introductions to as well. For a couple of them flew out, so we're really, really appreciative of their time. We want this to be an amazing learning experience, a networking experience, an engaging conversation. So feel free, everyone's safe, everyone has a voice. So we're really appreciative of any questions you may have for the panelists as we get to that portion. That being said, I want to say hi to everybody online. We're also live streaming. So for those folks who could not make it and who are live streaming, we welcome you to the live stream. That being said, I want to do just a quick transition before I pass it to T to introduce Linda from Austin Women in Technologies, who's AWT is a supporting sponsor of this event, and she'll talk a little bit about AWT and then toss it back to me, and I'll toss it to T. Thank you.
Thank you, everybody. I'm Linda Nguyen from Austin Women in Technology. We are a community of women in technology and provide a place for women to grow, learn, and connect. We have about 700 members, give or take. And we have monthly happy hours and a bunch of other events as well. For example, in July, we're about to have a hiring event. And then we're also about to have a wellness event as well. And then we also partner with a lot of other technology nonprofits around town. For example, Austin Technology Council, Austin Forum in Technology, Austin AI Alliance, Better Business Bureau. We have a lot of partnerships. And so we also co-host events with our partners, and we're going to have a co-hosted event with Austin Technology Council, and that panel is going to be on AI. I think every panel is kind of sort of talking about AI right now, but so if you are interested in learning more, come find me, and we're online, and memberships are only $80, and that usually gets you into pretty much most of our events. We also have a mentorship program and Slack channel, and we also host an annual tech conference, which we just had in May. But that's about it.
Awesome. Thank you, Linda. Thank you again for your support. Awesome. All right, let's jump in. I'm going to pass it on to our moderator T of ORCA Computing, have a fantastic panel and discussion.
I already have.
Okay, switch.
All right. Thank you, Marcia. And of course, thank you to the American Physical Society for putting this together and for having us all here tonight. Good evening, everyone. My name is Thien-An. Most people call me T. I'm the CTO at ORCA Computing, and I'll be your moderator here tonight. So a little bit about where I'm coming from, because I think it's relevant to why I care about this topic so much. My background is in integrated photonics with some signal processing, semiconductors, and software mixed in. I earned my PhD here at UT, and I've lived in Austin for nearly 2 decades now, so it means something to me personally that we're able to have this conversation in the city tonight. At ORCA, we build photonic quantum computers. We've now deployed more than 10 systems to the field. They are data center ready. They are in standard rack form factors, and they run real applications in areas like generative AI, including work in de novo vaccine development and materials discovery. So when we talk about engineering the leap from the lab to the data center, it's not an abstract concept to me. It's something that myself and my team, we work on every day. And just like all of you, I'm excited to learn from the experience and perspective of all of the great panelists that we have here tonight. Before we begin, I want to acknowledge that, first of all, the world of quantum right now is extremely dynamic. And justifiably, there are many heated discussions and a lot of competition around what the best qubit modality is, what the best error correction protocol is, and what's the most efficient algorithm. And that's all great. But that's not really what tonight is about. So tonight we're looking beyond the qubit counts, and we're looking beyond algorithms to discuss something that I think has been woefully underrepresented, which is the infrastructure challenge. The engineering, the system, the policies, and the deployment reality of bringing quantum technologies into industrial settings. So behind me, you can see the evolution of quantum classical deployments in 3 stages. The first one we have is the standalone deployment. So if you think back to the first pictures or mentions of quantum computers around, let's say, 2016 or so, you'll remember seeing a picture that's something like this, right? And indeed, this is what most people still picture when they imagine a quantum computer today. A large, isolated system housed independently and accessed remotely over a network. There are many companies that have showed these pictures over the years in their public announcements. And indeed, these systems showcase remarkable physics. But they suffer from high latency for hybrid workloads and have no real integration with classical compute. And so that makes it so that these systems are very impractical to deploy at scale in industrial settings. The second stage, which is where most companies are working towards now, is the co-located deployment. So for this, the quantum processing units sit near the classical computing resources and critically within the same environment. So this scenario features local connectivity, lower latency, and efficient hybrid workflows where quantum and classical work together in real time. And this is where ORCA operates today. And finally, for the last stage of integration, we have on-node integration. And this is where the QPU will be directly embedded within classical computing nodes. This, of course, offers the tightest coupling and the lowest possible latency. Tonight, when we discuss engineering the leap from the lab into a data center, we'll actually be focusing on the second stage. In particular, what challenges quantum computing companies and data centers will face as we bring these 2 technologies closer together. How will they affect each other, and what we need to develop or put in place in order to be ready. Very few companies today have delivered systems that operate in co-located data center environments. ORCA is one of them, but we're early. But this is the direction of travel. This is inevitable for quantum computers to meaningfully contribute to society. And as more and more organizations develop systems that are capable of co-location, they're going to run into the same set of infrastructure problems, and those problems are going to stress the existing data center infrastructure in ways it was never designed to handle. And so in my opinion, the best way to solve the problem is by first better understanding the true nature of the issue and by taking preventative measures. And so for tonight, rather than jumping straight into open discussion, I've asked each of our panelists to take a couple minutes to introduce themselves, their organization, and then share their honest perspective on the state of quantum today and what they think it's actually going to take to bring these quantum systems into data centers. That way you'll all be able to better understand the unique and valuable perspective that each one of our panelists brings to the discussion. And then following that round of introduction, we'll begin our regular panel discussion and end by opening up the floor a bit to some questions that we may have from different members of the audience. We'll be ordering the panelists starting with those closest to the lab end of the spectrum and end with those closest to the engineering challenges faced by data centers. And so with that, we'll start with Professor Xiuling from UT. Professor Lee is a Truchard Foundation Chair in Electrical and Computer Engineering at UT Austin, and is also the co-director of the Texas Quantum Institute.
Brighter. Okay, so welcome to Austin for those of you, especially students that travel from other places and from out of state. So I'm a professor. I'm a professor in electrical and computer engineering, and I teach semiconductors, physics and fab. So what we're doing was quantum. And with that, 2 years ago, April 2024, UT decided to put all these different kinds of researchers under the same umbrella called Texas Quantum Institute, TQI, and the members of this institute include people from all different departments. It's initially it was physics and engineering, and now we have chemistry, material science, mechanical, of course, computer science, and all kinds of disciplines, and we put people under 4 different pillars: algorithms, materials, metrology, and systems. As we'll discuss today, so other than qubits, everything else is actually classical to enable this infrastructure. So we need people who have the expertise of all different areas to come together and work on this, and so we can actually find real problems and get real better quantum computers than high performance computing and for actual practical application. And you can find people on those for each thrust on our website. And one of the questions I think we're going to continue to discuss today is and how do you benchmark quantum computing with HPC? And I have a quote from the DARPA program. It's called the DARPA QBI, Quantum Benchmarking Initiative. And what they're saying is by they gave a timeline, I think it's by 2033, can any quantum computing approach achieve utility scale operation? So what that means is the value quantum computers brings in has to exceed its cost. If you use that as a benchmark, what DARPA is doing right now is trying to evaluate the different modalities, including superconducting, neutral atoms, the trapped ions, the photons, all these different modalities, which is, I have a pointer here. Nope. This is in this table. So with that, so what can you actually achieve fault tolerant, long-term, fully error-corrected system? Quantum is noisy. So how do you actually apply these quantum error corrections and really achieve something that's going to last and continue to compute without errors? So that's the goal. So we're going to discuss how we get there. And before I end, I just want to emphasize more, which is listed in this table. If you look at the materials, the electronics, the optics, and everything else, this supporting infrastructure that's needed, we need everybody. We need people to be trained on all these different aspects so we can actually work together to make this a reality. Thank you.
Thank you. All right, thank you. Next up is Dr. Zach Burkley. Dr. Burkley is a senior staff scientist at Photonics, and his career spanned from fundamental physics to chip tape-outs and practical quantum systems.
Everyone hear me all right? All right, thanks everyone for coming out. Thank you, Professor Lee. Thanks for moderating and inviting me here. And Marsha, I don't know where you are in the room right now, and APS, thank you for organizing this. So yeah, my name is Zach Burkley. I'm a senior staff scientist at Photonics. And my journey is building what I personally think is one of the most important supporting infrastructure of quantum systems, which are the laser systems, these complex optical microsystems to control your quantum system.
Can you move it closer?
Is that better?
No. Maybe you can borrow a mic.
background was starting in academia and in quantum physics in Colorado State University, where I built a complex precision laser system to study hydrogen. It's fundamentally the simplest quantum system to test if we really understand quantum physics. In these pictures, I didn't, the line with T actually matched his graph, his pictures very well. You can imagine here on the left, this is standalone deployment. We had to build a complex precision laser to study quantum. And that whole picture on the left, the right side of that was the precision laser system. You have 3-5 semiconductor lasers, fiber amplifiers, control electronics, nonlinear frequency conversion. It took up a lot of space. Then I went to, I would say, my postdoc, where I did co-located deployment of laser systems with quantum devices. Here, though, we had to build a portable laser system. Imagine a European U-Haul that you could fit your laser in and take it to a particle accelerator, Paul Scherrer Institute, where you could study quantum systems that were like hydrogen, but they're kind of exotic atoms. It's called helium. And lastly, I've now joined Beacon Photonics. We're trying to take this whole complex optical microsystem and put it on a heterogeneous integrated photonics platform. Here on the right, we have a picture of the screen spiral. This is a solid-state erbium-built waveguide amplifier. We're pumping it with a 3-5 semiconductor chip that's in the same package, all in this butterfly package. And we're trying to make these complex systems manufacturable and scalable. Why I think that's really exciting is now what you can do is you take those complex laser labs that took up all this space to create these precision laser systems with multiple wavelengths. You can print them on a wafer in a domestic foundry. This is our vision in Beacon. We can imagine you can print hundreds of thousands of these microsystems on a single wafer. And you can print 50, hundreds of these wafers at a time at these foundries. And here's a picture of the stack of wafers we have at our company. This is really exciting. It allows us to scale these laser systems, but I think it produces some really exciting challenges that we'll talk about tonight, such as how do we characterize these laser systems at scale? How do you measure the frequency noise of a laser, the ring of a laser? All of this is kind of unique knowledge that not a lot of people have. How do you automate that for thousands of devices? And then lastly, how do you package it with the fiber optics, the control electronics, or any other supporting infrastructure into a nice compact package that you can put in one of these racks in a data center? How do you do that at scale and robustly? I think there's some challenges that this new technology is creating, and we'll talk a little bit about tonight. Thank you.
Great, thanks, Ed. Dr. Brian Mattis is next. Dr. Mattis is currently the Senior Director of Nanofabrication at Photonic Inc. As you may have seen in the news, they recently closed a massive round, so congratulations, Brian. Brian's background spans Intel's leading edge nodes, custom foundry work, and integrated photonics for both optical compute and quantum.
Cool, thank you, team. Okay, so thanks for coming. Most of my perspective tonight is going to be based around how you make the chips that go into these systems. That's foundries, it's labs. How do you take something that is special and try to scale it into something that can go to utility scale? And there's a lot of conflicts with that. So I spent a lot of my career in big fabs, small fabs, custom fabs, all trying to build different things. And now quantum's trying to enter that world and trying to have a manufacturable process, but every single company has its own flavor. So I guess a little background about my world right now in Photonic. I'm building chips, which is what I do. But our flavor of this is a cross between silicon spin and silicon photonics. So it's a cross between the two most common flavors of quantum. For us, our world operates in a manufactured defect for silicon spin that's interrogated optically. And the whole point of photonics playing on this is to have distributed quantum, so that you can have not all your cryostats all in one building. You can actually transmit entangled photons over miles and miles and miles. And we've actually even managed to demonstrate that already. Having entangled photons travel over a metropolitan backbone of fiber. So from my perspective, for not just Photonic, but for almost every quantum company out there, is there's going to be big challenges as we try to mass manufacture these chips. And there's a lot of money going into the foundries to do so. But the challenge is the fragmented requirements. So unlike the world of CMOS, where you can have PDKs, the process design kits, to try to run a flavor of CMOS and you know what the outputs are, almost every single quantum company is trying to do things differently, and that's not really compatible with high volume manufacturing. There's not a lot of sharing they can have. So a lot of my perspective on this is it's usually, what we have out there is usually a poor fit with commercial platforms. What you can get off the shelf now in multi-project wafer runs is just not really what most companies need to prove out their technology. So it's that jump from being able to do things in a lab or a university clean room and then trying to actually scale that is really challenging because there's not many good places to do it unless you have buckets of money and find your own fab like Thien-An Nguyen. So, so there's also a mismatch with high volume foundry economics. So foundries generally run tens and thousands of wafers a week. And to build these quantum systems, you need handfuls of chips, maybe thousands of chips. That's not going to fill a fab. The fabs run when they're full. Fabs like to be full because of the depreciation of equipment. So it's kind of a conflict of saying we want a fab, a real foundry to run quantum chips, but the number of quantum chips we're asking for is nowhere near what they run for CMOS or any other major technology. So that's kind of a bridge we have to cross. And there's not a clear answer right now. There's a lot of money flowing into these corners, but we'll see how that turns out. And then one more thing is, you can say, can you do custom foundry work? And again, a lot of quantum companies are going this route, but the choices for that are decreasing in this world. As more companies get bought, more companies merge, so we're getting this really large barrier from proof of concept, which a lot of startups can do in the lab, to having a place to actually scale and build it out to build utility scale.
Thank you, Brian. Now I'll ask Dr. Kyle Thompson to come up. Dr. Thompson is the founder and CTO of Maybell Quantum Industries, and he'll be bringing his background in cryogenic engineering, quantum device physics, and systems integration to the discussion today.
I moved into more of an aerospace and mechanical engineering setting, and one of the founding principles for Maybell as a company was to try to merge those two mindsets together, to take the deep tech that's required for a lot of quantum computing applications, and then take into account all of the more modern engineering processes and techniques, so that you can take a very bespoke type of manufacturing into something that can go into a data center or mass production, and really bring down the cost and bring up the quality. Sort of the same problem that everyone else is working on, but just from a different perspective. So, as far as what I think of the next 3 years for quantum computing, there's a lot of discussion about the qubit as being the bottleneck for where quantum computing is today. We're talking about our photons, our transmons, and all of that. But in order to move into bespoke quantum, into the future of quantum, we have to solve all these challenges that we're talking about today. You have to find out how to get a foundry that will make qubits at a high enough quality at a small scale that it makes sense for the qubit manufacturer to invest in that and make that and still have a qubit come out again that's high quality. And this is ubiquitous throughout the entire quantum industry, where we're trying to make this transition from today's scale to tomorrow's scale. And a lot of the companies I work with, some of them are photonics, some of them are superconducting, some of them are spin qubit. And you oftentimes see these bottlenecks along the way where there is no way of getting efficient quantum computing from a small scale to a large scale. And that's something that I put a lot of time and energy and research into, and I think we'll talk about today. And as a company, Maybell, our concentration is really going into that, going into figuring out how to use these manufacturing techniques to make things that will work for a technician that knows nothing about quantum so that they can run these systems. And I think I'll bring a little bit of that perspective.
Great, thank you. We have Chris Sutton. Chris is the quantum control system architect at Keysight. Chris works on what he describes as the central commercialization challenge, which is turning quantum computers into operable, deployable, and integratable infrastructure.
Thank you for the introduction. So yes, I'm Chris. I'm happy to be here. background's actually in residential construction. I was a carpenter for 20 years. And so I thought for sure that when I wound up in university when I was in my 30s that I would just go for engineering. I wound up in a physics laboratory and I just kind of stole my heart. So my graduate degrees in applied physics. I worked in the superconducting circuits laboratory. I worked in design, fabricate, and characterize superconducting circuits. And then I currently work as a systems architect for Keysight. We're working on the next generation control system. Some of the nearer term applications for the control system will be actually in these kind of hybrid compute environments, so like supercomputer compute clusters, HPC, Datacenter AI. They're looking to us kind of as a nascent accelerator, and they're interested in kind of exploring the possibilities there across all the modalities. So I cheated a little bit here. Marcia asked for a kind of one sentence, like what's the main problem that we might face as system integrators here, and you can see that I have much more on that, but what I would say the one sentence version of the slide is that the main problem will be in kind of establishing a multidisciplinary research and development feedback loop that we kind of work to integrate these two different types of computing. So thank you.
Great, thank you so much. Okay, thank you. So with that, we'll move on to our panel discussion. And our first topic of the night is how quantum systems can move from research to real-world deployment. And we'll start with this question. So from your perspective, what is the one main obstruction to bringing quantum research into industrial settings today? And I know that maybe it was addressed earlier, but really just the one key punchy thing, right, that everything rests on. Zach, we'll start with you.
All right. To be really concise with it, I think the supporting infrastructure and technology to operate quantum systems is very complicated and hard for people to use without a lot of training and degree. So, like we're hearing from some of the panelists up here, to create these systems such that they can be operated without even a person around or without someone with a training or a PhD in quantum physics, and operate remotely and reliably over long time scales with very little attention. And right now, I just think the supporting technologies such as laser systems or cryogenics and electronics, all these things are not there yet, and I think that's one of the challenges.
Yeah, no, absolutely. Yeah, one thing about putting these systems into data centers too is that you'll find that there's not enough space for all the PhDs to be crowded around. So there's a logistical problem involved with this. Brian?
I think it's still just a matter of maturity, right? So any new technology like this, it's still in the teething phases. It's just, the rest of it will come, but it takes a lot longer than people think to get it to a place where it is standalone and can just be run with its eyes closed. And that's because people are still optimizing everything. Once you have something that's a good enough solution to be production, you can hand it off. But right now, I think almost every company is still tweaking and still tuning it to where you can't be hands off.
So one of the things that I've noticed a lot from interacting with a large number of working with a large number of companies that have tried to figure out what their scaling plan would be, is all of the companies seem to have a plan for what a scaled quantum computer looks like. And within the expertise within that company, they are experts at building the GPU, building a quantum processor. And the more I interact with them, the more gaps I find in sort of the interfaces between that company and their RF infrastructure, that company and their signal provider, that company and their cryogenic provider, that company and the facilities that they're going to put their next quantum computer in. And the way these companies are structured, and they're very incentivized to be experts in what they're doing because they don't have so much money to hire people and hire resources. They are really trying to think about this, but those interfaces seem to be a weak point, and I don't think there's a lot of incentive from the rest of the world to sort of shore that up. And I think that that's a big area where quantum is lacking and could use a little bit of outside guidance as those interfaces.
I agree. I think the way I would put it is like quantum's kind of becoming right size as we start to try to integrate into these fully developed, I won't say fully, but much more developed technologies. And so I think typically we're comparing ourselves to ourselves, like physics to physics, qubits to qubits, and we're saying, how does this modality work and what does it compare to other kind of quantum systems? When in reality, if we want to integrate with this existing technology, we need to start comparing ourselves to them. And so we're doing that right now. We're kind of understanding where we come in at power consumption and facility requirements and different things like that. But Tori mentioned it, by long-standing admins who know nothing about quantum, and everything needs to be abstract. And one of the first problems that we're finding is that actually we don't have a scheduler that integrates seamlessly. And so that's something that someone really needs to just be able to kind of push a button, recognize quantum as a resource, a schedulable resource, and then let it perform its task at whatever the allotted time it is. And that's something that we're kind of working on now, but certainly falls into that category of something that needs to be negotiated.
Mm-hmm. Yeah, so we've heard a lot about how there's a lot of supporting systems, a lot of supporting engineering that needs to be more matured and matched to the quantum technologies in order to translate these technologies into these industrial settings. But I guess one thing that I'd be interested to hear about is also just on the front end of this, right? So going from cutting edge research in the universities, what kind of challenges do you see in translating some of the research that you and your colleagues are doing at the universities into maybe the first step of bringing it into industry?
So that question is not.
Oh, I think you need to wait a little bit. Yeah, there's a bit of a delay. I think it's good. No, it's not working. Okay, so just kidding.
Long enough. All right, that's so much. Thank you. I think that question should be asked regardless whether this is quantum technology or any other technology. And but in terms of quantum, I think it really depends on which modality we're talking about. And I'll just take superconducting qubit, which is the most mature out of all these photonic guys. Disagree with me. I'm actually a photonics person. But the superconducting qubit, how many qubits do you need? And how many dilution fridge, which is at millikelvin temperature, you can afford or can actually put in a data center? And if you think that's a scalability issue, what about neutral atoms? Those are easier to scale, but they're too slow. And there are so many different kinds of challenges with your questions from research to practical application. And every one of these technologies actually needs a lot of fundamental research. Putting on my hat, a professor doing fundamental research here. Our goal is de-risk all these different layers of this whole quantum stack. What could go wrong with your material? What could go wrong with your modules? And in between of all these, you mentioned the interface, integration, thermal management, the power consumption, and all these. I think it needs the fundamental. I always think these things need to be solved from both ends. You come from top down, and you do from bottom up, and all the problems you can envision. If you come from different aspects, and maybe you solve them before it becomes a roadblock barrier for the technology to commercialize at scale.
Mm-hmm. Yeah, actually, you bring up a really good point, which I think is not necessarily unique to quantum, but the problem is exacerbated in quantum, which is that we are extrapolating from these experiments in the lab and building full systems out of them. And I don't think that, and the systems are so complex and so complicated that we don't really understand the operational parameters within which the qubits need to operate either. I think to some extent we do, but there's so much that we don't understand as we start bringing these technologies into industrial settings where there's a lot more electromagnetic interference, there's a lot more vibrations, there's weird thermal constraints that we wouldn't necessarily have thought about. So that's a really good point. Yeah, so I always like to say that quantum will be, when quantum is successful, when quantum is considered boring, right? But in order to get there, there's a lot of boring problems to solve, right? And a lot of these boring problems are related to more the engineering as opposed to the more interesting fundamental physics side of it. So what's the most boring, what is the most surprising boring problem that we're going to need to solve to bring these systems into data centers?
I'll go first. Yeah. Maybe if you remember from the picture I showed of the lab, above all the laser systems were boxes of custom electronics that took up just as much volume, really, for us in the lab. And getting all of these electronics to control your laser systems or these devices onto an ASIC, this is, I think, something that can be solved with existing technology.
but it's been very hard for us to find any funding because it's not an exciting thing. It's a boring thing to do. Who wants to fund it? So I think just in general, the systems engineering of these supporting electronic devices and other supporting infrastructure to propagate this complicated equipment, yeah, it's boring, but it needs to be done. Right. You always see we're going to make our photonic chip this small, plus electronics. Right. So yeah, everyone takes a picture of the small chip, and then there's the entire factory in the background. Yeah.
Yeah, I would say from my perspective, one of the most boring parts of it is for photonics probably is packaging. Photonic packaging is still really immature. It's just literally trying to glue a fiber to the side of the chip and making it stay there when you cool it down really cold. Right? It's silly, but because of the total loss budgets a lot of these systems have, it's one of the main pain points, and it's just really mechanical. And we think simple, but it's not. It's definitely not very sexy.
Yeah, I would actually say across the entire stack, there's all this research being done on the qubit, but there's also a ton of research that needs to be done on sort of a very fundamental level of how you just connect a fiber to a chip. And that's not just like engineering research. There's fundamental materials problems there. There's fundamental, like, how does the heat get out of the chip and into your plate? There's a thermal boundary that is a physics problem that is difficult to solve at these temperatures because all of a sudden your acoustic modes don't match. So when you're dealing with quantum, you're just in this regime where everything that's normally easy is no longer easy. And then you want to add on to that, we want to go from 100 qubits to 100,000 qubits. And now you need 100,000 wires connected and not breaking apart or not communicating to one another. So there's this huge fundamental issue that is associated with scale, especially scale in these very, very careful and controlled environments that have to be the way they are.
I think it's funny that we become animated at when we describe the most boring working on. I too feel kind of passionate about a couple things. I give two examples. So one, there's been some great work done by IQM lately, kind of as one of the first companies to be kind of integrating these systems, and they did a really good job with the write-up and explaining a lot of things. And one thing that was close to my heart, again as a carpenter, was that they discovered the size of the door only when they were trying to bring the refrigerator. And so I think it's a boring and some maybe seemingly obvious problem, but there's a lot to negotiate and a lot to overlook. And so I think that's one thing. And then another thing, there's so many different industries that we would call maybe quantum adjacent or that are kind of supporting these like quantum computing efforts. And one of them is like we have all this incredibly precise room temperature electronics, and we're connecting it with coaxial cables or the like that have temperature dependent EM properties. And so if we don't have control over the climate that's inside of these facilities, we're losing some of the precision that we kind of are taking for granted or assuming is a certain way and finding out the hard way that it's not. I would say those are kind of two like simple, boring problems that we face.
Yeah, no, that's a great example. And another parameter that not very many companies even consider until something breaks is just the fact that there's a load-bearing capacity for the floors of data centers, right? And that, as you saw in the first picture with the massive golden chandelier, those are very heavy systems. And so if you start needing to put in so many of these heavy systems, to go from 100 qubits to 100,000 qubits into one facility, you're literally going to break the data center, right? Like we're stressing the infrastructure to the point where there's physical damage to the buildings as well. Absolutely. I think some of us are a little bit more biased. We try to be not biased, but certainly, Kyle and Chris, you're a bit more agnostic to the modality. So, from your perspective, are certain modalities easier to bring into data centers than others? What's your feeling, or what are your thoughts on this? And what has your experience been in working with these companies?
So,
it's really here. It's hidden.
So this might come off perhaps as like totally biased because it is. I think one of the very first things that my company designed when we first started our company was we designed all of our systems, the same thing as ORCA actually, into 19 interacts with the data center in mind. So what we've done is we've made it so that our
Are there modalities that fit better and some that don't fit as well?
There are designs that fit better and designs that don't fit.
Okay.
But I think you can get them all.
Yeah, I think just to the point here before like modality becomes a competitive sport, I think really there are great collectives that are working to kind of standardize just things in general for quantum industries, and I think to your point about things just kind of fitting in, HPC and supercompute is not impressed with quantum unless we have some kind of value to them as an accelerator. If it doesn't fit through the door, if it doesn't fit the 19-inch rack, we become a burden. So in some ways, we know that we have a little bit of work to do, but in other ways we find like that actually the power requirements for superconducting are much, much lower than even some of the minimum requirements for like HPA Cray racks. We have maybe 1/4 the power requirement for our densest installation. So.
Oh.
I have a question.
Sure.
I think all of the quantum computing is based on transmons, right? Transmons, which are basically Cooper pairs, which require dilution refrigeration, which is in the millikelvin. Why can't you go to higher temperature superconductors that instead require liquid nitrogen instead of liquid helium?
So,
That's a business question.
I'm going to answer the question, but what I'll say is when we refer to modalities, that what we're referring to is actually different ways to realize a computational device using a physical system. So the transmon 100%, that's a type of superconducting qubit. It's exactly the way you described. If you can find a room temperature superconductor, please tell me first.
I'm talking about liquid nitrogen.
No, I completely understand. But so what we're trying to do is leverage existing techniques. I think that's kind of what we're all doing, no matter what the modality is.
Built in 2007, right?
Excuse me?
That technique has been around since 2007.
So when you talk about technique, what do you mean? The fabrication technique,
No,
or the cooling technique, or
use
the?
of liquid, using the low temperature device.
Yeah, so when you make a ceramic squid, which is sort of the fundamental part of a Joseph junction, they have a lot lower quality and they don't last as long. So it's really, really hard to make things at higher temperatures. But there are many, many room temperature warm
I'm not talking about room temperature.
No, but there's photonic quantum computing, which is what these guys work on right here. The quantum computing spans the entire temperature range, and there's a lot of trade-offs with quality versus temperature. You're talking about high temperature superconductors.
Are you talking about trapped ion systems?
That is another one, but I'm not talking necessarily about that.
Can I take a second answering
Oh, sure.
question? Yeah, the reason you need to be in millikelvin temperatures is, the superconductors are 1,000 times, 100 times higher transition temperature. It's not because of the transition temperature of the superconductor. It needs to be cold for thermal noise.
That's the lower the noise.
Yeah, so if you made them out of a higher temperature
Yeah.
superconductor, you still have to be at millikelvin temperature.
I think he's asking like why not go for the liquid instead of using the big boom and everything. I think I can answer also as well, because everybody agrees once you come into a specific technological path, with the computer, pretty much stuck. That's why IBMs of this world, superconducting, right, IonQs and everything else, because invested a lot of money. And if possible, Microsoft trying to do a topological qubit, which is not necessarily what is basic, but it's some sort of quasi-particle excitation intermediate. So that's the reason to show something that's stuck with it. It's difficult to, first of all, as a bunch of shareholders, using that right. So you're going to be needing that's why aside quantum right now, instead of saying, okay, we're going to do quantum computing, now they're saying infrastructure first, quantum computing second. It's not just because NVIDIA wants $2 billion, it's not part of it, but that's the case. If you commit to specific or technological path, whether it's quantum computing, or likely to not be stuck.
Yeah, and as a lot of people mentioned, right, it also depends on your modality of choice. So your question specifically is for superconductors, but as they mentioned, for photonics, we work at pretty much room temperature for most of the system, except for the detectors, which are liquid nitrogen cooled into the elements. So it depends on the technology. There's been a lot of companies that have proposed a lot of different architectures to overcome this fundamental issue. Okay. So let's move on to the second topic, which is the enabling infrastructure in hardware systems, right? Because as we mentioned, if we needed to install hundreds of thousands of these dilution refrigerators, it's going to be a big issue. So what are some specific challenges to deploying this quantum hardware into data centers?
So one of the challenges that I've come across with installing not just dilution refrigerators but other quantum types into large data centers is oftentimes there's a mismatch between efficiency. So for instance, if you're worried about the electrical efficiency or wall power efficiency of your quantum system, you need, say, 100,000 of these dilution refrigerators. It's really extremely efficient in order to make cooling power at large scales at work often. But when you start getting down to millikelvin, there are other requirements that are not necessarily power, helium-3, accessibility, the ability to do maintenance, turn one on, turn one off. So there's all these competing requirements that choose efficiency is good at large scale here, small scale here, and merging all of those together is a really difficult challenge.
Yeah, so as we get into the world where we do need to scale up the infrastructure to meet the requirements of a quantum computer, do you see that exposing these companies to any supply chain risks? And so what would these be?
Absolutely. There's supply chain risks up and down the entire supply chain. If you want to get really high quality superconducting coaxial cables, there's 3 companies in the world that makes them. If you want to get high quality copper, you have to go find a smelter that makes the copper. If you want to find enough helium-3 for a data center, you have to fly to the moon and mine it. Like there's challenges across the supply chain, top to bottom, that just have not been figured out.
A really wise person once told me that you should never have a startup that's based on other startups. And no, and that's really true across the case. Because of these specialized things that every single modality needs, and some of them need very different things, the supply chain for all the feeders just is very sparse, and you're gambling a lot, and it's not going to have much supply chain redundancy. And can those startups grow to support you as you grow? And these are major risks, and that keeps board members awake at night as well.
So what have your companies been doing to get in front of the supply chain risk?
Just sticking with the supply part of supply chain, there is an incredible amount of overlap between what we do and what we require in AI and data center and HPC. So we order early. That's the solution.
Yeah.
Steve from Photonics. We're working on creating recipes for our heterogeneous integrated photonics that can be made at scale at domestic foundries. So to take this out of academic fabs or small one-off fabrication facilities and put it into domestic foundries where we can do it at scale. But of course, some of the challenges we face there, I think as Brian maybe was mentioning earlier, is our scale, what's big for us, is not big for them. So getting a seat at the table to make some of the changes to the processes that are unique to our type of photonic devices is a challenge, and one that we'll be facing to really, to get any further and scale this.
Yeah. And so I think maybe we can learn something from Professor Lee here on that front, right? So how have you been tackling this in terms of being able to access the right components, access the right parts, or to, as Zach mentioned, right, get a seat at the table, even if your volumes are not as big as some like NVIDIA.
Yeah, thank you for asking that. I'm actually going to turn this question to the panel. Semiconductor industry has, for the last 5 years or so, has encountered so many of these problems like supply chains, especially with the geopolitical environment here. And some elements we just don't have it here. And the quantum industry is much smaller compared to the CMOS world and even the compound semiconductor laser. And every foundry capacity is sold out for the entire 2026, if not beyond. And do you guys envision quantum computing or communication industry get to that point anytime soon? Is it something you should plan now so you don't get to that part? And one more thing before I let them answer this: the volume. We're a university, we have no volume. Okay, we make one thing, a hero device, we publish. But I actually worked in a startup company before I was a professor, and we were making the VCSEL, the face recognition camera of your phone, and the preamplifier in your phone, and actually it's all 3.5. And that's the early 2000s, and the telecom was booming and everything, and so the supply and demand always changes, and when you don't have enough auto, okay, we'll take the professor's order, which is one way. When you're busy, nobody cares about the professors, because this is an industry that the profit margin is so small, because infrastructure is too expensive. So you need volume. So this volume thing as a startup versus the big elephant, the university, and all of these. University always has another way to deal with this, because we can pivot to something you don't care about until 2033. And for that, we are not really competing with the suppliers and all that. But we sometimes run into these issues also. So how are you guys preparing for these things? That's my question.
This is going to give Brian some PTSD, I think.
Yeah, it is exactly where it is right now, right? And I think even the most mature quantum company is not going to be filling their fab. Right? Tens of thousands of chips is a lot or two a month, especially 300 millimeter. And at the same time, the foundries that are out there, that are fully booked and have no interest in messing with their process, so some small quantum company can do something interesting. Trying to convince them to do otherwise is tricky. Yeah, go ahead.
Yeah, there was an announcement just yesterday or today from IBM that they're putting a 300 millimeter fab up in Albany for quantum. Do you know anything about that, or what kind of?
I do know, that's my world, so yes, I do know a lot about that, and it's actually a really interesting thing. So they're not putting in a new fab, they're taking their fab and putting a new label on it, because that's what fabs do. So the interesting thing there is, okay, cool, you have $1 billion. Which modality are you going to support? Now they've already come out and said they're going to focus on supercon because that's IBM's bread and butter. That's what they have been working on themselves. So it makes sense they got $1 billion to do what they were kind of only doing. The whole concept here is though they're going to make it more open for other folks trying to do supercon to get access to it. And it will be a more standardized process. It will be more vanilla. That's good for that modality. But if you're, for those doing that modality who want to do something a little different, how flexible will they be? To be determined. The other challenge with that, so GF was also, GlobalFoundries also got a big chunk of money for this too. The GF version is to do a quantum foundry to support more modalities, because as it stands right now, GlobalFoundries does have a photonic telecom datacom platform that's mostly irrelevant for most people in quantum, because it just doesn't do what we want it to do for pretty much any of us. So the question is, well, what kind of flexibility are they going to have? Because these companies are used to running, especially GlobalFoundries, are used to running fixed processors that they built from the ground up to run tens of thousands of wafers a day. And now you're asking them to do R&D that eventually results in a few handfuls of wafers. So do they actually want to do that? It's pretty different for the business model. How do they support that? How do they support this custom work? Because their engineers aren't used to that. So they've got a big bucket of money to do so. How they use it is going to be really interesting. How easy they are to engage with and be flexible for what all of us different companies would be asking for is going to be really interesting. I also think it's a little bit of the case, I'm on my soapbox here, but when politicians say, oh, we need to invest in quantum, who has the best lobbyists, right? You notice both of those companies are heavily based in New York State, right? That's not a coincidence. So it's politicians wanting to give money to try to accelerate this, but they don't quite know how. And so the other flip side of that bill was to actually take equity stakes in some of the big players in quantum.
So that's going to operate as a foundry for other external customers?
They say so, that's the plan, but we will, I'm very skeptical just because I don't think they know how to operate as a custom platform, how they're going to bring up custom platforms that are flexible enough for what everybody actually needs.
What does quantum computing really mean to Silicon Valley? It's understandable that you can't get any time in a 7 nanometer or 45 nanometer manufacturing $100 million two micron fabs should do the job. What am I misunderstanding?
Yeah, so I give you, my expertise has been in the photonic side for the most part, but in my world, you still need some of the precision you get with high-end lithography and low defectivity. So if you're doing a waveguide, you have to have low particle counts, and the higher the lithography tool you have, better performance you're going to get. Lower lineage, roughness, smaller taper tips to transition to other things. So you still want high-end equipment, but you can't use it.
You have to wait until everybody migrates to sub 1 nanometer, and then it'll be old fabs you can use.
Correct, but right now the push is to get quantum now. So we'll get to it.
Yeah, but following up, you really need, but you don't need the finest node. I mean, you can still be working at the 90 nanometer node or something instead of at the 2 nanometer node.
The short answer is it depends. It depends on each photonic platform, what they're doing, whether they're doing it silicon or silicon nitride or diamond or anything else, right? It just depends, but a lot of these systems, their budgets for their performance are really already at the edge of what's possible. And if you throw bad fab tools at it, you'll make it.
Okay. So I'm going to shift gears a little bit. And this question is for Professor Lee once again. So you mentioned that in order for you to get a seat at the table or get any capacity in working with these vendors and partners, you have to pivot to something that nobody cares about yet, but that people will care about soon, so that you're able to, in a sense, you need to be able to predict where the technology is heading, right? So in terms of quantum computers being deployed into these industrial settings, are you working on anything right now to solve some of the roadblocks that a lot of us will be facing in a couple of years?
Great question. Thank you. So we have two missions. One's education, workforce training. One's fundamental research, pre-competitive research. And of course, the fundamentalness depends on whether you're TIL 1, 2, 3, and all could be university driven. We don't have the scale, and so what we really want to do is, as I was saying, we de-risk at every level in the quantum stack, starting from materials. And one of the things we are working on, we work on spin defects, but we don't want to work on diamond because other people have better quality diamond, bulk diamond. And those diamonds are purer than any of your jewelry. And our gold is purer than any of your gold there. So we want to find, for example, the single photon emitters that actually can be integrated better than the current state of art. And another problem we're working on is transduction. I want to address one of the things, so it came up. We can make billions of transistors. It's a parallel process. How come we cannot make 10,000 qubits? Because qubit is fragile. It's noisy. It doesn't want to stay coherent. If it's decoherent, it's not going to be performing like a quantum bit for computation or any other performance. So making a lot of qubits is really difficult. So one of the research we're doing, starting from materials, is okay, I have 100 qubits here, I have 100 qubits there. Can I connect them optically with fiber? But that's at microwave frequency, and I want 1.35, 1.5 micron optical frequency. How are you going to do that? So there are lots of these long-term problems that the industry are not really working on yet. There's one company I know is working on this. So that's where university coming. We do pre-competitive research, but hopefully de-risk some of the challenges will not stop you when you get there.
Mm-hmm. Very cool. We'll get into this in a bit too, but I'm also curious from your perspective what it would take to then, in the future, translate some of that technology technology into startups, especially here in Texas. But we'll get to that in a minute. For the next question, for everyone here, if a major hyperscaler came to this panel right now and said they want to be quantum ready in 3 years, what's your advice? And the advice cannot be that they buy one of your systems. We'll just get that out of the way.
I was thinking a lot about this because I think sometimes we expect like profound answers, but like kind of looking at some of the like near-term implications of what is actual like commercial utility right now. I mean, you're really looking at some like quantitative analysts, some software engineers, and then a cloud compute platform, access to HPC or a quantum computer somewhere, and that kind of gets you in the realm of doing quantum research internally. And so it's not buy a land mass in Maine and build a data center. It's not actually such a profound investment. I think as maybe it sounds sometimes.
I think that's what I would suggest to them. There's, as we've heard, lots of modalities. We don't know which ones are going to be the successful ones or which are going to play out. I would recommend to build up these specific quantum modalities, each one of them, in your large corporation, and then integrate those, hire those scientists. I think we've seen recently Google just hired a whole bunch of neutral atom physicists from Boulder because they're building up a neutral atom team now. Again, they have the money to hire a neutral atom team, a supercon team, a photonics team, and start having them collaborate, integrate with the engineers and the people that know how the technology works at the company, so then you are ready and you can track which is the quantum ready technology that will win for that company. So that would be a conservative way to diversify and go about it.
Yeah, and in the future we'll use Professor Lee's technology to connect them all together.
Yeah, so for a conservative buildup, I'm not sure that's the way to do it. You can internalize all the capacity to go from n to n times 1,000 inside your own company, but that involves hiring a whole lot of internal resources and building up a lot. And that buildup is going to happen no matter what, but it doesn't necessarily, I'd say, have to happen within your own organization. I think another way a hyperscaler could come to you and they say, I want a utility scale quantum computer in 3 years, they have to build up their entire supply chain. They're going to be talking to companies that are building 10 of a thing now, and they're like, we need to build 10,000 of them in 3 years. They need to have long-term commitment to each of their supply chains that are critical for that buildup. So if I were, Google, IBM coming to a supplier and like, I need this in 3 years, I would start thinking about 5 years before and say, we need you to do this demonstration first year. That way, the year after that, we can commit to some kind of milestone-based contract to build up into some kind of scale number. But I really think building up your own internal supply chain is the way to do it.
Great.
Can I ask another question?
Sure.
Thank you. Well, quantum computing is very different from traditional. You can use 100 qubits right now to crack crypto code of fine code based on primes because it's an analog system. It's not a digital system. Am I wrong in what I'm saying? That it can become profitable right now for setting up and solving analog problems with small number of qubits.
I think there's a lot about what you said that is correct, but there's some nuance to it. There's incredible research on algorithms that are being developed every day by different research groups around the world. But the fundamental issue is that they have different underlying assumptions. And so the recent paper, I think you're maybe referencing one of the papers out of Google, but the recent paper on reducing the number of logical qubits needed to implement Shor's algorithm down into the thousands or hundreds of logical qubits, it assumes a certain degree of coherence and connectivity for the individual qubits that the current architectures don't support. So that's the reason why we don't already have that right now, and that's not why banks are not scrambling to catch up. But that being said, it could happen overnight. It will happen very quickly. It'll be very slow, and then it'll happen all at once. And so certainly a lot of organizations should be preparing for when these technologies will be.
Armageddon.
Sorry?
Armageddon.
Yeah, there's actually a name for it. It's called Q-Day. Yeah. Professor Lee, going back to what we were talking about earlier, the Texas Quantum Institute sits at the very interesting intersection between academia, industry, and government. And so, from your perspective, where is the federal and state investment misaligned with what you actually need?
Question for me.
Well, fair enough, but you can.
Okay. Actually, Texas Quantum Institute is just UT Austin's quantum research organization. We are university. We are not government. Well, we're state government. But we really try to position it in a way that's not siloed. An individual professor can work on a problem without collaborating or without getting to know what industry challenges are facing. So it all depends on the time horizon. If you're solving a problem that will be a roadblock for industry in 2 years, that's one thing, and if I'm talking about 2033, that's completely different things. But what we really try to advocate to the state government, and in many ways we work on federal grants all the time. We talk to some people at the federal level also, and we're advocating. For example, one of the things is I'm not betting on any modalities right now. Like you mentioned Google is longest time is superconducting qubit, but now they're throwing neutral atoms. You mentioned that, and so we want state government to support the fundamental research and workforce training across many types of disciplines in order to actually help stand up the ecosystem.
I can talk a little bit about it. Yeah, so you made a really good point earlier about pre-competitive development. Is that how you call it? Yeah. So we all, I think, are from different states, and different states will have different kind of funding models or opportunities. And so I think actually I'm from Massachusetts. They put together a collaborative. There's state investment there, and it seems to me more than invest in one particular modality, what they invested in is developing a higher level of public-private partnership. And so most of the university laboratories that they invested in, part of what they did is create a legitimate path for the public to have access to a fab facility or cryo test as a service or different things like that, so that there was more demand from the laboratory. This kind of talks a little bit about the point of having such a low volume coming out of some of these facilities, or a low demand, not getting you a seat at the table. And so I think in that way, they're quite well aligned with things that will help our state develop, and I think they have a good model for that. So, but I think it's oftentimes giving people equal access to the financial resources, and oftentimes it's just an announcement. And so if people don't know about it, they're going to be in their laboratory with their noses down, and they won't find out about it until late. So oftentimes what we see is that the person who gets the most funding is the loudest one or the only one in the room. And so I think in that way, perhaps kind of publicizing these types of funding opportunities in a different way, rather than kind of .gov website somewhere would be helpful. And there was a rep here earlier, so I mean we're excited to kind of see how Texas pans out, given the size of the pool that they're kind of able to dip into. So that's a great point.
So I'll just circle back to one of the things I talked about a little earlier. One of the places I see government involvement that would be really important is incentivizing or funding or in some way accelerating growth areas that are not incentivized by the private industry. So we were talking about this, Photonic, IBM, all these companies, they're incentivized to show that their qubits are the best, that they can connect them to the best, that they can do the best calculations with X number of qubits that they have. The infrastructure side is incentivized to build instruments and machines that people need right now. There's no incentive to figure out what's going to happen in 3 years. The manufacturing companies can't build out for 1 million qubits right now. They don't have the internal funding for that. Their internal structure for how the companies are built just can't support that kind of thing. The large hyperscalers of the world aren't necessarily asking for that last year or this year. So there's this huge gap between when the qubit is ready, like you said, it's going to go slow until it goes really fast. And if we wait for it to go really fast before we start building out any infrastructure, we're not going to have any of that infrastructure.
Which is actually exactly what we're seeing with the AI boom
Exactly.
right now.
AI is a perfect case, and I should have just drawn that analogy. That is smart.
Everything goes back to AI.
I'll add one extra point on that too, is that, I think in terms of the federal side, with this latest bill, they've jumped on and helped some companies. Texas is a bit behind, right, compared to the Eastern Seaboard, compared to Silicon Valley, or Colorado. Texas doesn't have that many quantum companies that I'm aware of. And so rather than going that route, building up the other parts that all these ones need, it's kind of a low-risk way of saying, well, all these companies are going to need cryostats, probably, or what other pieces they will need. Can Texas invest in that infrastructure so that all of these different quantum companies, whichever one wins, will still be coming to Texas in some way or another to get what they need?
That's a very good point. So I know that there is a bit of a mix in terms of the audience today, with a lot of people from UT and State University. And so for the last question, if you're advising a college student today who wants to be working in quantum computing in a couple of years, what would you advise that they study? And as a related question as well, right, where's the talent gap most acute in the industry?
Right. Yeah, it's a great question too. I mean, I'm right now working with a lot of really smart photonic and electrical engineers in my company, and really realizing I have a very fundamental experimental physicist training, but I would have loved to have complemented that a little bit more work with some of these software tools such as numerical, console, all these things that you need to, say, design the photonic chip and take it out, or these things you need to design a mechanical, thermal, stable system. So my advice would be to try to learn what these current tools that are being used in industry, because those are the most valuable people right now in our company. They have so much work to do, and it's very hard to find that talent at the moment. So yes, Schrodinger's cat, Griffith's quantum mechanics, all this fundamental quantum physics is great. We don't use that in these startups right now, for the most part on the hardware technical side. So complementing this engineering and hardware skills with kind of these fundamental physics skills would be advice I have. And also on that note, I forgot to say, very exciting times with Beacon. We are hiring. We just opened an office in Santa Barbara. We have our headquarters in Arlington, Virginia. If you're interested, please talk to me.
Do they need to know numerical?
That would be great.
I think, the obvious answer is usually physicists, but another one that is really coming out as important is mechanical engineers. Thermal modeling is a huge part of what we do, and we're pulling in people who aren't from quantum backgrounds to do it. And then as T mentioned before, with these giant systems crushing the floors of things, in our labs, we need civil engineers. It's kind of crazy to be working on qubits, but really the civil is a key part of making it happen.
Bigger doors, I guess.
Bigger doors and bigger ideas.
I think when I reiterate what everyone else has said, but maybe a little bit different, one of the things that I've noticed in my company is the people that seem to be most valuable are at the interfaces. It's an RF person that understands qubits, an RF person that understands cryogenics. It's someone that can have a deep expertise in one field, but also have a semi-deep expertise in an adjacent field. And I can give a couple of quick examples of it. I've gotten qubit modalities from large companies, ones that you guys know the name of. When you do the thermal model of what their qubit is asking for, at the bottom of the cryostat, they need a meter cube of copper in order to be tracked. You need to have people that sort of understand what they're doing and the consequences of what they do. So I think RF engineers that know physics, physicists that know mechanical engineering that know cryogenics, that is the most critical thing and most missing thing that I've found.
Brian stole my answer, so I'll give two examples. One hardware, one software. So from a hardware standpoint, I would say actually, period, from a student standpoint, your advisor's gonna tell you to do weird stuff. One of which will be to work out of Landau Lifshitz, which I haven't looked at since I graduated, but it's a fabulous book. But it's not like something that we use every day. But I would say sure, no task. Your advisor's gonna ask you to do some weird stuff, and you should just do it. So a personal example is I work tirelessly using ANSYS, not COMSOL. It's like similar to do EM modeling of these absorptive filters that actually use technology from aerospace and defense. And that was eventually productized, and when I went and visited Kyle's new office space, they have hundreds of them sitting in a pile there. So little did you know that I actually helped develop the fab process on those. But and that's a real thing that I never would have seen. It was just something that I was stuck in front of a computer running simulations on. The second one is, we don't really talk too much about this, but across all modalities, latency is an issue. We have a lot of things talking to a lot of other things, and we want to reduce the amount of time that it takes in order to get a kind of round trip loop. And so, from a software engineering standpoint, Python's great. Everyone should know kind of how to run a Jupyter notebook and understand pulse level control that way. But we're starting to kind of look to software engineers that are a little bit closer to the hardware, like Rust and other languages like that. So I think those are other areas, that are certainly of value.
Great, thank you. Marshall's reminding me now that we're out of time, so thank you so much, everyone. Thank you, Brian, Xiuling, Chris, Zach, and Kyle for donating your time tonight. And of course, thank you again to the American Physical Society for launching this wonderful series in Austin. And thank you to Marsha, Heather, and the rest of the team for all the amazing work you do in the background for putting together these events. These types of discussions are exactly what the gathering, what our community needs right now. And so thank you for doing that. And thank you to Linda and Austin Women in Technology for their partnership, and to Capital Factory for the space.
Final comments?
Thanks to the bartender.
Thank you.
Big thank you to T. He did a great job. Thank you very much, T. We really appreciate it. I echo your thoughts. Thank you so much to Professor Lee and Zach and Brian and Kyle and Chris. Thank you so much for being here. And thank you for carving the time to be here as well. As I mentioned, this series is ongoing. We've got another one in September on integrated optics and the AI data centers. So if you have time to stop by on September 10th, we'll notify you. Yeah, I mean, we really, really appreciate it. I think one of the things APS wants to do is to just make sure we continue these valuable discussions, and you have all the opportunity to connect and build out a great network of mentors or folks that you can talk to and reference in the physics space. Final logistics, yeah, we've got plenty of food. The bar is open. Please feel free. The speakers are here. This is a fantastic opportunity to continue to network with each other, ask them lots more questions. They're all amazing. We have amazing ducks. Our APS ducks is a little memento. We've got new ones, so please feel free to go ahead and grab something. And thank you. We'll send a survey. Thank you so much for being here. If you need any parking validation, just hit Heather at the front. Thank you for being here, and have a fantastic evening. Thanks, guys.
Yeah. Sorry for the